Welcome back to another episode of As the World Turns with your host, Mr. Spence. Hey, have you guys ever seen this before? This is an awesome program called QuickMan. You can download it for free off the internet. This thing here is called the Mandelbrot Set, and it's a fractal pattern. It has to do with complex numbers in the polar plane. Check this out. Where would you like to zoom in? Right there? Okay, let's do it. Let's get a little crazy today. Oh my heavens, look at that. Ain't that pretty? Oh, what do we got right here? Zooming in, zooming in. What else are we gonna find in here? Oh, I like this right here. Oh my word, look at that. Ain't that the prettiest thing you've seen today? Zoom, zoom, zoom. Find something kind of crazy in here. Deeper we go, the more crazy it gets. Wait, I think we've seen this before. Haven't we seen this before? Yes. Look at that. It's the same shape over and over and over again. Man, this thing is so cool. You can go back and you can like zoom in anywhere that you want to. Find some crazy patterns in there. Oh, ain't that funky? I like it. I like it a lot. Iterative. It's pretty sweet, isn't it? And you can change the colors if you want to. This one's angry. We can go with loud. We can go with earthy or smoky. Go with all kinds of crazy stuff here and keep zooming in and find all kinds of crazy patterns. This is complex numbers, people. This is stuff with complex numbers in the polar plane. It is awesome stuff. It is so cool. Oh yeah, back to the world. Okay. Well, we have to talk about what's going on in this next chapter. Sorry to take a little diversion, but I couldn't help myself. Chapter 9 is about polar coordinates and complex numbers. It's some awesome stuff. And by now, you keep seeing that we're touching the same kinds of things over and over again. There's going to be some correlations here among several areas of maths. Well, that's what pre-calculus is anyway, isn't it? We're going to include all these things when we get to calculus. Vectors, conic sections are in this chapter, complex number sets, and the polar coordinates. That we're going to graph complex numbers. That sounds crazy. Trigonometry is involved. Geometry, we're going to overlap all these areas and try to make more sense of it. You're going to see a lot of things that you've seen before, but now in maybe a new application. It won't be too terribly complicated, but there will be some new stuff that might blow your minds. And that's okay. That's okay. We're going to do lesson 911 here, polar coordinates. Our lesson objective that you should write down in your notes is we're going to graph points with polar coordinates. Oh, yeah. And here's what I would like you to do. I'm going to give you that sheet with the graphs on one side. I'd like you to take notes on the back of that polar graph paper. And you're going to do the guided practice on the front. Except for the number 3 guided practice, you can do those wherever. You can do it on either side. That's what you're going to bring to class. We're going to check is your graph paper and your guided practice 3 stuff. Got it? Now, this whole issue of polar graphs. So let's go into to the school, okay? Let's go zoom in there and strap on your seatbelt. North Valley Christian Schools. Well, I gotta change that one now, don't I? That's not what we are anymore. This should look kind of familiar, huh? But maybe if we put the grid on, we can see latitude and longitude, and it looks like a big bunch of squares, right? Squares, that seems more like we're looking at our normal coordinate grid, x's and y's. If we were going to go from here to the Laley's house, we'd have to go this way and that way. Or we could go in a straight line if we've got a quadcopter or something like that. But we would typically have to go across these grid lines. Is there a place on Earth that we've got polar coordinates, or it looks like a polar graph? It looks like that paper stuff that I gave you, like this? Can you think of a place on Earth that's like that? I know I can. Yep. That's why I tagged it right here in the North Pole. So here we go. Grid. Wait a second. Polar graph paper, people. Check that out. We've got radiuses going around in circles, and we got these lines going out at different angles. Isn't that cool? That on the Earth, you've got polar graph paper? Man, polar graph paper is so kicking awesome. You have no idea. So we do live in a world that is full of both the coordinate grid system and polar graphs. Sprinkler systems, they're going to go at angles. You go to the store to put in your irrigation system, you're going to have to think about this. How many degrees does the thing rotate, and how far out does it go depending on the pressure? You have lots of this kind of stuff in the real world. What we want to do here is explore just kind of the basics about the way that we draw these things, the way that we represent them in space. And we're used to rectangular coordinates with x and y going at 90-degree angles to each other. That was the Cartesian plane. But we're going to do something different called the Argand plane. That's polar coordinates, like the polar graph paper. And that one's represented as a radius at an angle. So this will look really familiar. I mean, we did this kind of thing in our vector chapter. But I'm going to use some terms eventually. I want you to get used to the terms right now. That the radius part of it is like absolute value with vectors, or we had the magnitude, but this time we're going to call it the modulus. That's a fancy word that they use in polar coordinates for the radius part, how long the thing is. Or at least how far out we go. And then the angle part is called the argument. That's going to come in handy when we start multiplying these things by each other and squaring and taking the roots of things. We're going to want to use the words modulus and argument. So start using them now so that we're not confused later on. Okay, so in your book, if you would, go ahead and open up to lesson 9.1 and look at those first pages. I think it's page 534. We've got the basic setup. You've got rectangular, which works in squares from the origin, going out along the x-axis and then up from the y-axis and finding our place where those two lines will intersect, and then defining that point in the coordinate system x, y. But we've got then this other thing where we start with this point here called the pole, and then we draw a line straight out. There's the line straight out this way, where we used our unit circle angle 0. And then we rotate that radius out to some other stopping point. So I'll go ahead and do that thing here. I got my original point, and then I rotate it out, and somewhere around here I'll stop. And we measure then the radius here, which is, we count how many concentric circles we got. 1, 2, 3, 4. I went out to 4, and I went to an angle of 72.4 degrees. So there's my modulus and my argument. And I think you know that if you have a positive radius, we'll have this on the next page. If you have a positive radius, you go this way. If you had a negative radius, you'd start out this way. And then rotations this way are positive rotations, and rotations this way are negative rotations. So our little graph thing doesn't show that. We are used to that with the unit circle going to the left and to the right. So this is the way that polar graphs are set up. Instead of, you are going to see kind of the original grid there as we got north, south, east, and west. And I haven't labeled them 90, 180, 270, and we know that 360 is in there as well. But now we go out in concentric circles to find our radius. So we're going to do some of these. They're going to ask you to, example 1, to graph polar coordinates. And our first one would be to graph a point they're going to call A. And the modulus is 2, and the radius is 45. So let me go ahead. I'm going to put a new point on here. Point, and I'm going to go out to 2 for starters. Put that point out to 2. And then I'm just going to grab that point. Yeah, that point. Oh, maybe I can't grab it. I would grab that point and I would rotate it. Let's see if it was stuck on there. I'm going to go out to 45 degrees. We go, and that point would end up right here, correct? Wouldn't stay there. It would move over to here. Piece of cake. We're in a positive direction. We can do that in radians as well. And your fancy paper is in radians. Let's say that I want to go ahead and draw that in on this one. I'll pick red. Let's say that I started off with negative 1.5. Okay, so there's 1 and there's a 1.5. Maybe this isn't going to let me do that on this paper here. Yeah, with the pen. Nope, it's not going to let me do that on here. All right, well, it was a good thought. I would go out first to negative 1.5, right about there, and then I would rotate 2 pi over 3 radians. How far is that? How far is 2 pi over 3 radians in the positive direction? Well, that's 90 and 30. It's 120 degrees. So I go here to here, and I'd stop right about there, and I'd draw my dot, and I'd label it B. So there we are. It would be out here. But I went the radius direction first, and then I did my rotation. It was a positive rotation, so I went counterclockwise. Your guided practice, you're going to have to label D, E, and F. And 2 are in radians, and 1 of them is in degrees. But let me share with you my little method, the madness here. The method that I think is probably the easiest to work with is you start from the pole, you start from the origin, you move R units along the x-axis. If you're going to have, I guess let's just say positive R, change that. Positive R, you're going to move to the right. If you've got a negative R, you're going to move to the left along the x-axis. Once you find that spot, then number 2, you're going to rotate it however many degrees or radians. If the rotation is a positive rotation that you're supposed to do, a positive angle, you're going to go counterclockwise, same way that we did unit circle stuff. And negative angle, you're going to go clockwise. And then you draw the dot in. That's it. You label the point on the graph. That's how complicated this one gets. Example 2 is going to do the same thing to graph the point on the polar grid. Same thing, you got a modulus and you've got an angle. You're going to be doing example 2 guided practice 2A and 2B. I want to see kind of like the process going out along the x-axis, left or right, and then rotating either clockwise or counterclockwise. Then any of these points can be given a different identity. And see, in rectangular coordinate system, each point has a unique set of coordinates. There's only 1, 2, negative 2. But this is not true in a polar coordinate system. A given angle has an infinitely many coterminal angles. Right? You could go 46.1 degrees, or you could go 360 plus 46.1 degrees, and you end up at the same place. You could go around the circle twice, or 5 times, or 100 times. Or you could go in the reverse direction once, or twice, or 1,000 times. So you've got a whole bunch of definitions for the same spot. You could even start off by going in the negative direction. You go over here, and then let's say that we started off with our point over here. We said that was a negative 4, and then we rotate it a negative 90 degrees. We'd end up here, which would be the same thing as going in a positive 4 direction and a positive 90 degree angle. But it ends up at the same place. This seems to be the thing that students get stuck on. I don't know why, but that's just the case of thinking got to go out along the x-axis first, either positive or negative, and then I can rotate either positively or negatively to get up to this place. So we said I could have gone 4 and positive 90 degrees. I could have gone 4 and negative 270 degrees to get up to here. I could have gone negative 4, negative 90 degrees to get there. I could have gone negative 4 and a negative 270 degrees to get there. I could have gone 4 and 360 plus 90 degrees. I could have gone 4 and negative 360 and another negative 270. I could have gone a whole bunch of different things. So your guided practice 3 is you're just going to come up with several different ways to write the same endpoint. Several different ways of writing where we stop. Ways to get there. Kind of maybe instructions to get there. If I was back here in this stuff and I was trying to find out how to get from North Valley Christian, formerly known as North Valley Christian Schools, to Barrett Laley's house, I could describe several different ways to get there. I could leave the parking lot and I could go along the 32 to the west until I got to road and a half, and I could go up this way and hopefully don't get shot. If I go this way, I could turn to the left and then turn to the left again on N and turn to the left again there on 12 and get to the Leleys. I could get there in several different ways. I could get in a helicopter and I could fly this way. I could go to Starbucks first. Ooh, I'm going to go over to the far. I'm going to go to Dutch Brothers first and then go to the Leleys. But I could still get to the same ending spot. So there you go. I probably spent way too much time on this, but you're going to be using that graph paper that I gave you. And you're going to be putting the dots in wherever they go, and we'll check those when you get back to class. Sounds like a good deal? Yeah, it is. It is a good deal. You're so lucky.